Applications of configuration. In this module, you describe configuration overview, state the capabilities offered by configuration, and their application to real design situations, define entity and port mapping, list different forms of configuration, and analyze the application issues for each of these forms. To build up a hierarchy in VHDL, we need to declare components and instantiate them to provide the sockets into which we plug chips. The chip in this case is an entity and a single architecture of that entity which together define the interface and behavior. The VHDL construct that plugs the entity/architecture into the component socket is the configuration statement. The code on the slide depicts a full adder built using two half adders as shown on the right. The architecture of the full adder contains the component declaration and instantiation of the half adder which forms the socket. Which entity/architecture pair of half adder is plugged into this socket is determined by the configuration statement which we see in the coming slides. As we saw in the previous slide, the VHDL construct that plugs the entity/architecture into the component socket is the configuration statement. The configuration statement defines which entity and the architecture of that entity will be used to plug into a particular component socket. You can think of it as a parts list for the design. When the names and port lists of the component and the entity are identical, we don't need to write an explicit configuration. The simulator can link the component and entity automatically. This is called a default configuration. If you are using a default configuration but have more than one architecture for an entity, the last architecture to be compiled is the one that is used. Default configurations are sometimes not suitable. If we need to map different instances of a component to different entities, or the names or port lists do not match, then we would need to explicitly write a configuration. Configurations are used to explicitly link the hierarchy. It selects specific entity/architecture pair for each component instance. Explicit configurations are not generally supported by synthesis tools. Configurations are very useful in simulation, however, allowing you to quickly build various different views of your design for simulation. You can consider it as a build list for hierarchy. The full configuration is not shown here, but the fragment shows how we could link a specific entity and architecture to every instantiation of the component half-add. This statement specifies to link entity architecture pair HA to instance U1 of half-add. If we need to map different instances of a component to different entities, or if the names or port lists do not match, then we would need to explicitly write a configuration. Mapping capabilities enable models from different designers, using different names, types, etc. to be used. For example, each of the two instances of the half-adder can be mapped to different entities using different names, types etc. using configuration. The configuration CFG_fulladd_delay is associated with the entity fulladd, and configures the architecture structural. It tells us, for all instantiations of the component half-add, use the entity named HA, with the architecture timed, from the library work. Map port X on the entity HA to port A on half-add, HA port Y to half-add port B, etc. Note, named port mapping is more readable than positional. The first N4 matches for all, the second N4 matches for structural. Use indentation to keep track. Note that we could configure the individual instantiations of half-add to different entities/architectures using separate clauses as shown. We can also use an others clause, which is useful for multiple instantiations. Configurations are quite powerful and are becoming increasingly important for large complex system simulations. In this example, we need a component comp map with input and output ports of type unsigned and length 8. We have a model comp gen with generic sized ports, but of the wrong type, i.e., std_logic_vector type. We see that using configuration we can specify the correct generic value and perform type conversion on the ports in the port map. We could create a number of different configurations, each of which build a different simulation view of our system. There are three major different organizations of configuration possible: 1. Top-level configuration that references all components/entities, 2. Configuration that references other configurations, and 3. Architecture configurations. We will look at these in the next few slides using the example shown in the diagram. Each block in the diagram contains 2 rows. The first one denotes the entity name, and the second row denotes the architecture associated with it. The first style of configuration organization is the single top-level configuration. In the example, the architecture RTL of entity pnet read contains a further hierarchy, read frame, and write data components which require configuring. Therefore, once we have specified using entity pnet read and architecture RTL for all instantiations of the component pnet read, we must then configure the components in architecture RTL. We enclose the configuration of these components with, for RTL, and for. These are statements to signify that they are part of the architecture RTL hierarchy. This is followed by the configurations for the remaining entities pnet write and CPU. This configuration method has the benefit that you have in one place the specification of how the whole hierarchy is built. Note in this example, all the components are being configured with design units from the library mylib referenced by the library statement. If our hierarchical models are in different libraries, then we would need additional library statements to reference the different libraries. In Style 2, we see that we can reference other configuration design units in a configuration statement. Here the configuration of the architecture RTL of pnet read has been created in a new configuration design unit configuration pnet read RTL. In this design unit, we specify the entity architecture pair to be used by the read frame and write data component socket. We can now reference this configuration for pnet read in the original configuration, with use configuration. This is followed by configuration for pnet write and CPU components. Note that we are specifying the library into which the configuration or entity/architecture design units have been compiled. In Style 3, we see that we can also add configuration information to an architecture. The architecture configuration can be used in each hierarchical block that instantiates components. Note that the architecture must still contain declarations for each component. Port and generic maps can be added to the architecture configuration too, for example we have seen in the full add design previously. This method means that the configuration design unit itself is not required, and the simulation can be invoked on the top-level entity. Note that the architecture must be edited and recompiled to change the configuration information. Let us look at the pros and cons of different configuration organizations. Default configurations are easy to use but restrictive. The top-level configuration is the most common and provides the most flexibility. Architecture configurations are less flexible and has more compilation overhead, as changing the hierarchy requires recompilation of the architecture. For large designs which have a number of engineers working on separate hierarchical blocks, it can be useful to have separate configurations for each of these blocks which are referenced by a top-level configuration. Each engineer can then maintain an up-to-date configuration describing their block which can easily be referenced by other engineers wishing to run a simulation of the whole design. Having a separate configuration for each entity is not very common because this leads to a large number of design unit files, causing design management problems. From VHDL 93, configuration information can be included in a component instantiation. No component declaration is required in the architecture. Instead of instantiating a component declared in the architecture, we can directly instantiate an entity/architecture pair, or configuration. Since these are direct instantiations built into the architecture will need to be edited and recompiled to modify the design configuration. Note that positional port mapping is best to use in direct instantiations. Compilation errors may be seen if a named association is used, since the compiler may not be able to see declarations for the entity ports X, Y, S, and C. Here, we see that the full adder design directly instantiates half adder along with the configuration information. Also, no half adder component is declared before instantiation. Let us summarize this module. A configuration specifies how to link the hierarchy. It allows the selection of entities/architecture, and the library design units to be taken. We can use default configurations under the restrictions of name matching, only one entity/architecture to choose from, only one library to choose from, and if design hierarchies are for synthesis. Configurations are not widely supported by synthesis tools. Specific configurations allow us to link models from different designers, from different libraries, using different names, containing generics, etc. Default configurations are generally used for design hierarchies intended for synthesis, and specific configurations are generally used to construct simulation environments to verify the design.